The pleasure of the third year in a row the blockchain research series. I see a lot of old faces and a lot of new faces, and it's a pleasure to see a very large audience. The purpose of this series started like 2 years ago, exactly 2 years ago, in October of 2017. It was like to promote research in the classical community. So it's not one of these series that we're saying that we're going to cure cancer or how great our company is, right? So it was very important for us as academics, of course, especially by place like fields, to demonstrate the relationship between mathematics, science, research, and blockchain, and vice versa, because the area of blockchain is an area that it does need to incubate further research. This is the first attendance of the year. We're going to have 3 more attendances, maybe 4. The next one is going to be in early December by a fellow from MIT. And what a great pleasure to have today Michael Zargham coming from San Francisco, correct? Yes. Yeah, although he originally is from upstate New York, so he sympathizes with the weather. He's the founder and CEO of BlockScience, an engineering, R&D, and analytics firm combining systems theory, computational social science, and empirical economics to improve the way we design, develop, operate, and govern economic systems. He holds a PhD in systems engineering from the University of Pennsylvania, where he worked on dynamic resource allocation and decentralized networks. The research team at BlockScience has supported startups and small and medium enterprises, has produced the open source software called CAD, which stands for Complex Adaptive Dynamics Computer-Aided Design, and continues to publish academic papers to support the work that they do as individuals and as a venture. The title of this talk is Blockchain Network Science and Dynamical Systems, and before I start, I want to thank, apart from thanking Fields for giving us this space again for the 3rd year in a row, and also financial support in air and hotel and travel of the speakers that I have this year. I want to thank Novera that helps in terms of gathering. York University is going to provide, and most likely they'll be running a talk after New York in March, I believe. And also the Department of Electrical Computer Engineering, where I come from, will also provide sponsorship for gathering this event. And of course, all the audience, like the guys, come every year and multiply and support this exercise. And also Henry, because after 2 years, I found a partner in crime to allocate not only his money but his time to organize Henry King from Zurich, York University, to organize this series. So, warm welcome to
Thank you for having me. So these slides are going to be a little different from most of the ones that I have online from talks because I didn't take the math out. I even put some back in, which was really exciting for me. So we're going to start with motivation anyway. So I talk a lot about complex systems because they have sort of dynamic feedback in them. And this means that the things that we do and the things that we create influence the things that we do, and this makes it actually quite difficult to understand how a system is going to behave in a sort of standard draw a box around the system and analyze it perspective. We kind of move back into the domain of, dynamic feedback. I'm a control theorist actually by education. I have a systems engineering PhD, but I worked on dynamic decentralized optimization and resource allocation problems, which is just basically code for math problems for doing mostly anything. I like packet routing. I did some coordination of sort of commodity type flows across networks, multi-commodity flows, and eventually just sort of wandered off into industry to learn how to apply what I knew and found blockchain. And as a result, we found ourselves in my team designing economic systems, which quickly brings us to this quote from Hayek, which is that the task of economics is actually to help us understand effectively the limits of what we can design. So rather than doing some magical mathematics can allow us to predict the future in crazy ways that we know aren't true, we're actually just going to examine those limits and use the tools to engineer things effectively. So The other side of this is actually what it can do. And I like this quote from Zen and the Art of Motorcycle Maintenance because it highlights the fact that if we don't go down to the complex systems level, if we don't look at the mathematical structure of the problem, we're likely to just reproduce what we had before. And in the case of blockchain, this means that if we just build on decentralized networks, the kinds of institutions that we have in the world without them, we're going to get more of the same, just on a slightly different substrate. And so for that, again, it's really important for us to be able to explore computationally, analytically, the things that we are building. So from a technical perspective, I tend to work backwards from general systems theory down through reasoning about complex systems, recognizing that we have social systems which are complex, economic systems are a subset of social systems, and then we get to these crypto-economic systems which are actually dynamic, networked, adaptive, multi-scale stochastic systems, lots of big math words. Actually, for once, I can appreciate that my audience knows what these words mean. We'll start with dynamical systems. So we can interpret a blockchain network as sort of a system of maintaining the state of a ledger. And that system is actually second order in the sense that what we're looking at when we look at transactions is the state change. And the state, which we infer from the state change, is updating each step. And we're actually checking the state transitions more than we're actually checking the states. And in the paper for the, it's an applied network science paper, hopefully forthcoming, recently submitted with co-authors from the University of Pennsylvania and Protocol Labs, we actually laid out this sort of formal set of definitions. So we have this actual trajectory of states occurring. And when you build on that, you can start to reason about mechanisms as sort of state update operators. And this is great because then transactions become sort of the realized state transitions. And the mechanisms are essentially the operators that take the current state, the action taken, and give you the new state. So we're starting to recognize these as discrete time dynamical systems. And in fact, depending on whether you think about it as each individual transaction or a whole block, it's still just different timescales. So you have a snapshot of the state at a block, but actually if you open up a block and look at the transaction order, you have an even finer grained discrete time dynamical system. So what can we do with this? Well, for starters, there's this real nonlinearity here. The order matters a lot. And so this is where things like front running come from. If you realize that it's a sequence of compositions, then there's a really severe nonlinearity here. If I jump order and my action affects the state and this next action is dependent on the state, this means that, jumping ahead of line in, say, a decentralized exchange will have massive ramifications on the effect of my transaction. And so in order to actually really reason about blockchain networks in a sort of, I'd say, mathematically rigorous way, we actually have to move beyond thinking about things in static representations towards dynamical representations. So here we simply see that we can have a state update as a composition of actions, and this gives us this first useful outcome from the mathematics. There's a strong distinction between what can happen and what will happen. So when you define a dynamical system, there's a concept called a configuration space, right? It's this space that you can actually get to. In the physical world and in robotics, we deal with this when there are like rods and real configurations like physical objects that restrict the number of points that are valid. So if you have like an arm, then if that arm has a length, then the position of the points at the end of the arm, it's not actually 2 points in 3 dimensions, it's 2 points in 3 dimensions minus a linear restriction that gives you a 5-dimensional configuration space, and so on. Now, in the economics world, we generally don't have anything that we can rely on that concretely as the rod. Like, sure, you could smash the rod and break the invariant about its length. Here, you have a smart contract, say, and it enforces a hard business logic rule that's inviolable, and these provide restrictions on this sort of economic space. And I think from a technical perspective, it's important to remember the vast majority of the things we engineer are actually built up from restrictions. So your Newton's laws are restrictions. They're equality constraints. F equals ma. You have Kirchhoff's laws. You have V equals IR. And these linear equalities combined with the things that we engineer actually roll up to more complex things. In crypto, one of the biggest problems we have is that we only really see realization. So one pass of the system over time, but what we're designing are actually like reachable spaces. We are saying you can do these things under these conditions, and then we can say because of that, analytically, only these things can happen. And that's the design space that we actually have. It's not about making things happen. We can't force a realization, but we can design a reachable space. So moving forward, though, all right, so we have these paths through these reachable spaces, but they're determined in effect by strategies of agents. So in controls, we would call this a control policy. It says, here's the state I'm in. Maybe I have some private beliefs. Maybe I have some private utilities, and I'm going to make a computation and take an action under some conditions. And so these U's in this model are the actions taken by the agents. And if we want to encode an autonomous system, we need to say that the actions are a direct consequence of observations of the state, possibly some exogenous signals, but ultimately this is our feedback loop in like a controlled theoretic frame. We've got our outside signals, we've got the policies that determine the actions, mechanisms that tell us the consequence of our actions dependent on the state. We may have some full system state that's not totally observable, some facts that either aren't on chain, you don't have the right to access that data, maybe they're off chain, and they resolve to some observable system data, which in turn influences the decisions of future agents. Important thing here, we don't assume some rational hypothesis or even some bounded rational hypothesis. We simply say, our agents, they have some utility function. We don't know what it is. Maybe it's convex. That would be convenient for analysis. But ultimately, we want to see this loop happen without the interference of something outside of our model so that we can run these simulations, these tests, or do analytic closed form analysis that tells us something about our configuration space, our reachable space. So I want to show you an example. This is going to be Uniswap if die pair from launch. What you're seeing is actually a system comprised of a handful of dimensions. So DAI is effectively a reserve currency here because it's fiat equivalent, at least in theory. Ethereum is the asset that's being traded against DAI. And what you see with this square is actually a area that remains constant up to fees whenever there's a swap. So if you move along the curve instead of moving the curve, then the area of the square stays constant. This is actually quite important because inside of a Uniswap, there's this simple rule that basically defines what a swap is, and it means that you are preserving the product of DAI and Ethereum. That means that the tangent to that point is actually the spot price. And the only reason the curve is moving is because this thing is accumulating liquidity. And that means that either someone is injecting liquidity to get some uni supply, which is essentially the liquidity token that you would have if you're effectively invested in this. And the way that you get out of it is by burning those tokens to take some of the liquidity out of it. What's cool about this is that this isn't just the data from the contract. This is actually a CAD model of the smart contract driven by the real behavioral data to actually represent the system as a differential equation and backtest the differential equation to show that it reproduces the real phenomena observed in the Ethereum network. So part 2, we're going to talk about network science. So in the context of economics, the reason why the network science stuff starts to come in, at least for me, is that we talk in terms of micro foundations of macroeconomic models. We also more generally talk about the interscale feedback between the behaviors of the agents and the sort of behaviors of the system itself. So there's a thing called the Lucas critique, which is from, I'm not sure what year, but it basically is a primary criticism of the sort of Keynesian macroeconomic models that people use to assess economies on a large scale. And there was a big movement in the direction of agent-based models. And actually, as an engineer, we just sort of say, well, all models kind of have the same form. You've got some outside world that we care about. You've got some internal parts that sort of make up the system. And so we sort of just say, like, any practical systems exercise starts by asking, what's my macro context? What's my micro foundation? And then we follow modeling first principles to find something that's useful for solving the problem at hand. And so building off the sort of economics criticisms and synthesizing it with engineering systems, engineering best practices, we can sort of start to dive into our crypto networks again. So here we have a model of a crypto network in 3 layers. You've got entities, which are essentially businesses, people, etc. We've got economic addresses, accounts. These are sort of pseudonymous nodes in an economic network. And then we've got nodes, which are actual nodes, computation and communication. And there's a sort of multi-graph here because entities have links to each other. It's a real world relationship. They also have the ability to control the keys of an account. So I have an edge. If I have the private keys, I can sign a transaction and act as though I'm this address. And I can also operate a node in a peer-to-peer network. And this is sort of interesting because we've really lifted the problem. I see often this issue where people talk about the network. Which network are they talking about? Is it the whole network? Is it the economic network? Is it the peer-to-peer computation network? Until you disambiguate this, you could make lots of claims that are, questionably true or false. So, talking about the social system, the top level, I have this graph. It's a community network that someone made. The DGov community has started to curate this. All of the projects working on decentralized governance. And actually, I just sent an email to the team about a few more links to add to it. But it really points out how interconnected the network of people in this space are, and obviously it's a subgraph. There's people working on things other than DGov, but it's really important to remember that top level system is also a non-trivial network system whose shape affects the way people behave. So if we step into the economic layer, we get to one of my sort of favorite canonical problems, which is a network flow problem. There are quite a few of these in my PhD thesis, actually, and they're represented by this incidence matrix where there's a directed graph and there's a there's a vertices by edge matrix, and you put ones and minus ones in to show the directed flow of the edge, and it shows up in this simple dynamical system. And when that is the input matrix, we get some really interesting properties. And I guess I will show those properties in a moment. So it's a network flow problem, and we have a quick look at this is the Ethereum network in late 2014, I believe, top 1,000 nodes. And this is the flows of just ETH going between these nodes. There's also new nodes appearing. The red ones are external accounts. The sort of red to yellow is external, with red meaning more holdings, and the blue to green is smart contracts. And they, again, blue being less and I believe green being more holdings. The idea here is that this is a dynamic network. It's over time, an edge shows up when there's a flow of ETH across from account to account. And we have to remember that dynamic networks have very interesting behaviors. They're not simple, even if they are linear systems as described in my model, when they become time varying, interesting properties can emerge. So the third layer in my diagram was the peer-to-peer network, and here we kind of go back to our formal definitions, and we basically say that we are responsible for maintaining a state of the system, but we're going to have disagreements. It's actually not a true state of the world. There's a bunch of beliefs by each node about the true state of the world, and that's not actually just the true state of the world. It's actually a whole trajectory of the dynamical system. A blockchain, since it's the states and state transitions all the way back to Genesis, is actually a trajectory. But we kind of have this multiverse problem going on because every node could potentially have their own copy of the whole history of the world. That sounds pretty bad, but we can resolve it relatively easily. When you think about a consensus protocol in this case, it's just a mapping. It says, I have a trajectory, you have a trajectory. We use this rule to resolve whose is right. And as long as we adhere to it, then we actually do get consensus. In a proof of work setting, sort of Nakamoto consensus style, this is going to be probabilistic, but it's pretty easy to argue that if you get a two different ones, that the probability of the sum of all of the work that was used to create that trajectory is not going to be equal, because the amount of work itself was essentially a random variable. And so you add up a whole bunch of those, and you compare any two, even if they're the same height, you're going to have more work on one than the other. You're going to get a resolution here. The issue being you need a little bit of time to be sure that there's a low probability that a future one isn't going to come and force a reorg. I'm a big fan of the ongoing work to create basically finality blockchains, ones that have this non-probabilistic certainty. But in general, what matters is that we can resolve this sort of this trajectory or that trajectory in a deterministic way, even though there's a potential for disagreements among the nodes. An interesting thing about Bitcoin as an example, or also anything that was sort of modeled after it for minting supply. So if we take our dynamical system representation, we can actually collapse it and show that no double spends alone is sufficient for guaranteeing the convergence of the sum of all tokens. This may sound obvious. A lot of people think it sounds obvious because we all know and believe that this number is fixed, that we're never going to have more than 21 million Bitcoin. But turns out that with a peer-to-peer system, we're not really guaranteed that until we prove it. Like, you've got a bunch of individual nodes maintaining their own state and this, generation functionally decentralized minting of new rewards to someone based on the minting protocols. And that's sort of being injected into the economic network as newly minted tokens. And while the sum of all the newly minted tokens converges, we're still following a peer-to-peer protocol and money is flowing around. And you can actually write an explicit proof over the dynamics of this system that shows that the actual sum as a output is conserved. And we did this in a paper that the one I mentioned before, the paper that we submitted to Applied Network Science. And then sort of for some more computational flavor, here's a price dynamics on a computational model where you can see the halving points. So this had the same schedule as Bitcoin with the halving periods, and we actually had a look at the way the halving periods cause spikes in the sort of speculative behaviors, because right before a halving, you're about to have a change in the rate at which new supply is generated that's perceived by the public and influences the decisions in the model of the secondary markets. Which takes us to computational economics. So we built some models with our CAD software, and in particular, this one is part of our tutorials. We call the robot and marbles. It involves robots managing piles of marbles and sharing them with each other for different reasons, different desires. We've got this sort of agent-based model where we have 3 types of strategies. The strategies are state dependent, and the result is basically chaos. And I say this because the rules are actually very simple, but because there are new robots arriving, which is the case with our blockchain networks, right? We've got new accounts showing up, and they have non-trivial but relatively simple strategies. We get interaction effects. So here's a video of one of these simulations running. At each time period, a new robot shows up. They have some number of marbles, they have some strategy profile, and they just interact. And I kind of both do this to highlight the method, but also to highlight this sort of emergent complexity of these systems. We really can't make strong claims about what's going to happen, because even here you get greedy robots that don't get a ton of marbles because they're insulated by the fair ones, or you get giving robots that actually end up with quite a few marbles because they're insulated by they're insulated by the fair ones. So the network topology, which is changing, actually has an incredible effect on the outcome, not just the strategies. So another kind of network system that shows up in our crypto systems are networks of smart contracts themselves. So anyone who's familiar with the DeFi ecosystem is used to seeing like one smart contract using tokens or even functions that are exposed by another. So you've got like Compound interacting with DAI, and you've got DAI moving to a multi-collateral setting where it's taking other assets to collateralize to mint new. DAI is a fiat equivalent stablecoin, algorithmic, produced by an entity called MakerDAO. It's the sort of backbone of DeFi. And what I'm pointing out here is that each smart contract has its own state variables and its own state transfer functions or mechanisms. And when you start to interconnect them, you get a sort of systemic risk almost, right? It's not immediately clear that we get strong properties, even if the individual contracts have strong properties, because they're interconnected. I can call a function, which calls a function, which moves an asset, all of which are essentially in different contracts. And when we look at that network, that functional network, we can see some cool stuff. So here's an example from CryptoKitties. CryptoKitties smart contracts, they had a really interesting feature. They paid agents to give birth to cats. This may sound silly, but turns out smart contracts, they're not active, they're passive. So you might have taken the action to, sort of combine two cats to create a new one, but it's going to be, so many blocks later that can happen, and someone has to take the active transaction to give birth to it. And they actually had in the contract a reward in Ether for whichever contract made that transaction, which led to an entire ecosystem of sort of bot subcontractors. You could say these were some of the earliest keepers in the sense that they weren't part of the UX of the game, but they were part of the back end of the platform. And what's really interesting about this is not only did people show up to write bots to detect when this needed to be done and to call that transaction, they actually wrote new smart contracts to do this more efficiently, including using the gas token procedure to keep their costs low. So we actually did analysis a year ago and looked at the both the smart contracts that were doing this and how they were coupled by which contracts were interacting with them. So we got a sense of, okay, there's a handful of smart contracts and a handful of external accounts using these smart contracts. And there's this hard shift from blue to orange when we saw external accounts making this call go away and mostly see these specialized smart contracts, which we called midwives, doing the work. But this is an emergent behavior. That second smart contract wasn't there. It grew up out of the need. So this brings us to a new question, which is what happens when we have agents who are interacting in an ecosystem with different mechanisms? So most game theory kind of looks at the relatively static, sometimes dynamic analysis around a single mechanism. And that's great. You can sort of define a Nash equilibrium or even sort of a basin of attraction. But if you have multiple mechanisms, and you have lots of agents who are able to act on multiple mechanisms with some shared interactive sort of effect on the state, then there's always a risk that someone's going to go over on one side and take some actions on a smart contract to create a scenario they can exploit on another contract. And if you're familiar with sort of hybrid systems or switch systems, they have continuous dynamics and you have switching rules potentially controlled by an external system or adversary. You would see that you can actually drive a stable system unstable just by giving an adversary switching control. And because these systems are totally actor driven. So there's no passive activities in smart contracts. This is essentially saying that if you prove a particular mechanism is stable in the sense that it has some equilibrium, and you introduce some other mechanisms and interweave them, there's this ability of the agent to have a strategy that's not just over each, but is mixed. And that means essentially playing a switching game, which largely negates the ability to basically make proofs that are one mechanism. We're kind of exploring this further, but in a computational sense, we deal with this in our designs with conservation laws. Because it turns out that if you enforce a conservation law for all states, then your contract basically can't have this conservation law violated by composition with another one. I write a smart contract, every legal action in every valid state preserves a value function or an invariant, then it doesn't really matter how that action is taken, whether an agent takes it directly, whether it's taken through another smart contract. There's no way to violate this property. And that trick is sort of embedded in Uniswap, in bonding curves, and we're going to see more of it. And I think we're going to see more of it in a more complex way because it's a bit like writing your own laws of physics in a smart contract framework. So is you kind of generalize this and try to do sort of more sophisticated design work, you can introduce a concept of a Lyapunov function, which isn't just about maintaining a particular invariant. It's about actually constructing your own generalized energy function and writing arguments about how particular actions affect that energy. And this is sort of the version of stability that is the most powerful. It's used in multi-agent robotics. It can be used in nonlinear control theory. And in fact, I suspect we're coming to an age of sort of Lyapunov economic theory, although it'll take some effort from the mathematicians in the room to bring this to full applicability. So bringing it to full applicability is about understanding the engineering context. I like to talk a lot about cyberphysical systems. This is a sort of large-scale infrastructural engineering discipline, works on things like power grids. Here's the thing. Power grids don't actually exist. They exist as compositions of many things rolled up into a sort of hyper object that's all of the substations and wires and houses and power plants and people using them. And that's why we sort of see this as, feedback systems with humans in the loop, economics in the loop, network, distributed. This slide is from the Ptolemy project at Berkeley, a cyberphysical systems simulation and sort of validation verification framework. But what I note here is that all of these properties kind of line up for crypto. We've got the cybersecurity aspects, we've got the humans in the loop, we've got this massive array of applications. And a big part of what drove me to found the firm I founded was the complete and utter absence of the sort of yellow-orange middle part here. The sort of validation, verification, design methods, simulation tools, etc. And so when I sort of realized that crypto had this sort of same character and was largely absent the equivalent toolkits, and not just tools, but methods and best practices, that's kind of what I set out to do. And so we have to briefly review what sort of engineering is comprised of. And in our case, we sort of focus on the design phase, but engineering, at least on larger scale infrastructure, not only is there multiple kinds of technical expertise, electrical, mechanical, computer, etc., we actually have to build things and integrate them, synthesize them, and sort of make sure that they meet the top level requirements. They need to basically be right at the technical specification level, but they also have to be managed for their whole life cycle, right? You don't just build a bridge and hope it stays up. You have to be concerned about the conditions under which it stays up, managing it, maintaining it. And what that looks like for a crypto economic system may be different than what it looks like for a bridge. But once you manage the complexity of a system to the point that the end users don't really know that they're using it. So you manage to solve the UX problem in crypto, and we've got cryptographic networks securing money flows, contractual executions, etc. You kind of have an obligation to make sure the systems are safe because there's no explicit consent to like the work, right? You drive over a bridge. Every time you drive over it, you don't stop and think, wow, do I really want to drive over this bridge? And because of this, we view this as much more of a public good, a sort of economic and data infrastructure that our like society is going to kind of grow up on and around in many of the same ways that, you know, roads were a networked infrastructure that affected the way that people and trade flowed. You know, power grids are an example I like to use, but also even the air transportation network affected things. You know, freight and sort of ocean networks affected things. Our, you know, water infrastructures affected the way that we act. And actually, pretty much networked infrastructures, as far as I can tell, are among the most substantial things towards rewiring the way humans interact with each other. And every time there's a pretty high degree of abstraction. Like the technical problem solving happens, but most of the people who experience its benefits, no idea that it's there. And so when that happens, we rely on this kind of procedure to make sure that this is done in a way that really supports those people's well-being, not just the well-being of the people who created it. So, shoot. We lost it. There we go. Cool. All right. So I tend to talk about these things in terms of sort of vertical integration. So it's easy to get kind of focused on the technology, the economics, the social systems, but in the sort of data tech that we're dealing with, we really have this systems layers that start with the data that we trust to be true. Now, this can be content addressable DHTs, it can be blockchain networks, it can be a whole host of cryptographically secured databases and or structures of any kind, but until we have that, no amount of secure computation does us much good, because if we can't trust the inputs to the computation, we can't trust the outputs to the computation. Takes us up to the level of cryptographically secured computation. These are, you know, virtual machines as state. Transactions are any change to the virtual machine, and now we can do computation and trust that it's valid on data that we trust that's valid. Moving up to these interaction patterns, this is starting to be a bit like business process automation. We write smart contracts that streamline the activities that we want to do or have been doing or would like to be able to do, but they were too much sort of attention overhead to be feasible. And those patterns, they sort of create that configuration space that I was talking about earlier. You have like rules about what one can do, and we're trying to sort of guide or sort of like create a nice like environment where it's easy to do the thing we want them to do, but we don't actually make them do anything, right? At the end of the day, the local agent behavior is their own, and we're not going to try to pretend like people are rational or that they're going to do pretty much what we want, period. The key is that it shouldn't really matter if you have the right interaction patterns and you have at least enough of an understanding of what's likely. You can start to get some general trends, value flows overall that match the desired. And this might seem like a reach, but this is also what happens with things like traffic systems, right? At the end of the day, you design the roads and they take people from point A to point B, which is a sort of interaction pattern. But we really don't know exactly when people are going to go, at least not at the individual level, but we can start to see aggregate patterns like traffic. We can maybe examine intersections with high incidence of accidents and re-engineer them to have fewer. And actually, this is often done with computational models. Seriously. There we go. Cool. So in terms of practically achieving emergent properties as a design goal, we tend to break problems down into the high-level requirements. What kind of emergent properties do we want? What's the representation or model of the system that's like useful or realistic in not in the sense that every single bit of fact is captured in it, but it's a good model in the sense that the things that are in focus are the things we care about, and the things that are out of focus don't really have a high bearing on the outcome of the system or on the outputs that we care about. And as we drill down into the system, we define subsystems and components recursively until we have everything that we need, and then we start implementing and integrating and building back up. And ultimately, after we've done the system verification and validation, we can deploy it and even potentially iterate on the system. Though a risk here is that these systems aren't particularly iterable. I tend to describe blockchain networks a bit more like mechanical systems in that the cost of changing them after they're deployed is very high. In fact, it's much higher than the cost of spending a couple extra cycles doing design validation, a couple extra cycles doing testing. And again, this is something that we see the larger the infrastructure gets, though whether if we're talking about satellites and airplanes or large scale power grids, the degree of testing that we tolerate even in our business decision making is much higher. The cost of failure is higher. The risk of harm from failure is higher. And so this kind of principled engineering process is part of how we engineer these sort of high complexity public goods. This really doesn't like me anymore. I think this might be busted. No? Let me just restart it. It's moving. Cool. Oh boy, we're going fast. Let's go back. Cool. All right. So what's the next most important question we have to ask, which is if this was built on models, who decided what the model was? And I always hazard to point out that all modeling choices are fundamentally subjective. Modeling is a creative act. And we have a tendency to get so used to using the same models that we start to forget that the modeling choice was subjective. And with computational social science systems, it's really important to be aware of this. This is because the subjective choices of the model designer have real bearing on the people in that system. And this has actually surfaced itself quite a bit in the sort of AI and AI ethics communities, where the data sets that you train on, for example, might have some systematic bias. That model doesn't somehow clean that bias out. In fact, it often institutionalizes it. Similarly, if you're doing a systems engineering exercise for a computational social system, if you inadvertently sort of represent something you didn't mean to, it will be captured and retained. If you actually sort of model a system as having certain objectives as its real value proposition, it's going to give you those things, even if it wasn't quite what you intended. So this sort of notion of algorithms not being purely objective just because they're computational is very critical for someone to participate in the design of a social system. I'm very confused. There we go. Cool. All right. So in practice, how do we do this scientifically? Well, we have analytical methods, and you saw a bit from me on formal configuration spaces, the possibility of using Lyapunov theory to help create attractive basins for systems even with multiple mechanisms. We have computational methods where we run simulations, and we have empirical methods where we make real observations of real data in a living system and use it to whether potentially govern the system, maintain the system, design future systems. And these are essentially the tools of an engineer and increasingly the tools of an economist. So we haven't seen much of this in the economics domain, but in a large part, this is due to the absence of sufficient observations and, in fact, the absence of models that are reliable at the sort of granular level that we're talking about. And the introduction of smart contracts actually makes that a lot more feasible because they give us these natural laws, these guarantees. And it's the way that we make inferences in systems, physical or otherwise, is to look at what we observed in the context of what we know to be true. And the great thing about crypto networks is now we have non-trivial statements, axioms that are given to us by our cryptographic security that we know to be true. So we can use more systematic inference methods than simply black box machine learning models. Cool. So last major section, computational business models. So CAD/CAD is the software that we built with my team. So when I was working in academia, I used MATLAB. And MATLAB was great, except for that it's kind of terrible. And since you guys have probably used it some, you know that it's basically good for designing and testing algorithms, especially in the context of physical systems. We used it for robotics. eventually the code would actually get compiled down to C and put on a board and used to actually operate something, which is actually also remarkably similar to what we do when we're designing systems for smart contracts, because you kind of have these computational constraints in robotics, right? You don't want to do too much communication or too much computation and burn all of the power that you have on board. You also want to be careful in the sensor network applications to not do too much communication if it's going to cost you a lot of energy. It's kind of fun. You get to port over some of these same concepts from numerical analysis to come up with, better fixed point approximations for the algorithms you want to implement. But at the end of the day, we want to do social science systems. And so those aren't really well supported in MATLAB, but they're awesome in the Python open source ecosystem. The entire data science community has been pumping this ecosystem full of awesome computational tools for analyzing social systems. And so CADCAD is actually just a Python package. You can pip install it, and we use it to run these dynamical systems. Now, this is kind of how it works. You've got a state, you've got action in response to state, you've got the output of the state update mechanisms, and you get a new state. We can do this in parallel and in series. And so here we basically see a chunk of one state update might be this, but we have the purple box is what's happening in parallel, and then there might be another subsystem that computes after, and then another one that computes after, and then we can bundle that step over step into a dynamical system. Now, this is really a stylized representation, but it tells you what's happening behind the scenes in CAD. This is a representation of an actual system that we built a model of, and this is sort of a stock and flow diagram in the style of business dynamics, like in John Sturman's textbook. I think it was early 2000s. There's a sort of school of thought that kind of goes back to Jay Forrester about these business dynamical systems. The issue I take with it was actually just that it was always very passive. It's like the world works like this. And we have a very active system where agents are observing the state and making choices in potentially very complex and interactive ways. So I substitute the sort of faucet for a diamond, and we actually have these as just essentially the U in our previous differential equations discussion. You can act here. You don't have to, maybe you don't. And if you don't, then nothing flows. And so we sort of get this event-driven version of a differential equation, but still represented structurally. And what's important is that the structure of this thing still has a really high bearing on what happens. It's sort of a configuration space as filter for behavior or input signal. This is from a project called Fairmint, and this is a continuous organization. You've got basically a startup spending money to achieve some business objectives and generating revenue, and there's some rules about the conditions under which they have to either buy into their bonding curve or potentially burn tokens they have previously bought from their bonding curve. You've got the middle, which is a bonding curve which serves as a sort of interface between the sort of outside economy and this inside startup. And then we have a secondary market, which is in fact a Uniswap instance between this continuous organization token and a fiat equivalent, likely DAI. This is actually a model on the right, which is functionally equivalent to the one that I simulated for you earlier. And some pretty interesting stuff happens if you get this coded up as a differential equation. But before you can actually get it coded up, we have to switch from viewing it in this sort of stock and flow differential equations structural view to something a bit logical. So here we now have our differential equations frame again. This time the top is the inputs. Some of them are stochastic or random environmental processes. Some of them are agent-based models acting in response to state. And some of them are internal policies coded into the system. In this case, those internal policies are of the form the C org must do something under certain conditions. It's actually legally enforced, not on chain because it's an active thing, but within reason for our simulations, we're going to assume that the C org does as they are committed to do. And in a pinch, we can also run A/B tests and ask sort of what happens if they don't. That layer interacts with the mechanisms that say, given this is what happens, at the actions level, then here is the change to the state. there's a sort of summary of the Statespace model here, and finally the sort of KPIs or measured objectives in the bottom level. And that allows us to generate simulations like this, single trajectory that has the bonding curve's buy price and its sell price, and in fact also the price at which it would pay out if it were closed at that moment. The close price is equal to the buy price, so you see green on top of blue. That was an algorithmic requirement on the design, and we simply see that it holds. Interestingly here, the market price bounces around quite a bit, starts to fall under certain circumstances, but we're not going to try to get into that right now. What I find interesting here is I can look at this in more of a state space view, so I've gotten rid of time. The fiat reserve is on the x-axis now, and it actually kind of exposes the shape of the bonding curve a little bit, because inside of this curve there's sort of a square root appearing, and that's because it's a bonding curve with its sort of it's probably not the right time to. We can talk about this after the talk if you're interested in more. It would take me more time than we have to go through the details. But what's important here is that we're able to look at the simulation in the context of our understanding of this analytical model. So we're not only able to see what happens, but we're actually able to reason about whether what happened makes sense given what we know about the analytical representation of the smart contracts. We also helped create some metrics. In this case, there's a market confidence metric. And ultimately, what we really care about is taking systems from design into deployment and through their life cycle. As I said, this isn't just about build the thing, design it, say, oh, it must be perfect, and let it go out in the world and hope. We have this idea that is also born out in the engineering discipline, where the design is actually also part of the maintenance equipment. So we can actually help simulate and then feed data through it. Now, this again kind of goes back to what I showed with the Uniswap model, where we actually had the Dynamical Systems model in CAD, but we didn't feed it with sort of simulated data. We feed it with measured data. And it's actually possible to do this in real time because the Python data science ecosystem actually supports real-time analytics. And so the equivalent in robotics is being able to do system identification. You have a parameterized model, and you're getting data in real time, and you're effectively learning the best estimate of the parameters of the model, which allows you to do projections that say things like, well, if the actions keep going as they are, maybe we're going to go here. If there's a big drop in the price for some exogenous shock, then like how might the system react? And actually get a somewhat reasonable answer, even if this hasn't happened in the past. And this is an important aspect about machine learning in general. If you don't have any structure in your model, generally a differential equation that carries the temporal dynamics, it's going to be really hard to learn anything about the future that isn't represented in the past. But if you have a differential equation combined with machine learning, this is how we make sort of realistic assessments about what might happen under conditions other than the ones that we've observed in the past. So we go about this using this type of overall architecture. Probably not going to go through it in detail, but feel free to ask me about it. It amounts to combining best practices in robotics with the best practices in analytics to say, I have some goals, I have some system plant, I have some models, and I feed the models with the data, and I produce decision support analytics. Now, in a robotics system, you'd have a direct feedback loop instead of a arrow to humans. But in these systems, again, they're decentralized systems. We're not going to necessarily run straight back to the network. We're going to make governance decisions informed by these models. So I talk about governance in the context of these sort of adaptive systems, or in particular, the feedback loops. In the control systems literature, as you move into this social systems control, you're getting into the domain of cybernetics. And in this case, I like to identify first my interaction patterns that give me what I can do. The community actually does something, and this is our sort of base action that we associate with smart contracts. When there's a feedback loop that's state dependent, that's automated, we get this sort of robotics-like state feedback term. Simple example of this is the Bitcoin difficulty controller. You've got rules about how to sort of win by hashing a bunch of, basically you play a hashing game. I guess I don't need to explain this in this group, but in fact, the hash rate, the higher your hash rate, the more likely you're going to be one who finds the block, win the rewards. It's great. But if everybody's doing this and pumping the hash rate, then we start finding blocks too fast. And the system has a secondary feedback controller that increases the difficulty to keep the hash rate on the 10-minute line, or at least on average. And this is actually an algorithmic feedback control that's responding to the state changes, which is responding to the actions of the miners. Now, Bitcoin doesn't have a particularly well-defined governance process. It's mostly just people arguing about whether to institute some minor code changes and basically never making any major code changes because they don't have any governance procedures and they don't really have an institution or community that's responsible for managing collective action. But many crypto networks, especially the ones that are aiming at sort of more real, like more use cases in the business world or trying to manage a large community that's got some cohesion, will have some sort of institutionalized governance process, which allows them to make changes to the interaction patterns or the feedback controls, which gives you one more outer loop. And for me, what's really important here is that this participation includes this community, because I view this as largely akin to the system being democratic. If it's fine that I'm subjected to these rules, as long as there's a feedback loop between me and the process that sets these rules. And it can be the interaction patterns, it can be some parameters. This is essentially the base case for what's a DAO, a decentralized autonomous organization. And what I point out when I talk about this is that we're not going to ignore the social system. We talked about the crypto networks as being people and the economic layer and the computational layer. And again, this is sort of people, governance, and population and community. Then we sort of have this economic activity that's these two, and we have some sort of lower level systems potentially realized through sort of low level computation protocols. As a control engineer, I tend to think of that as microcontrol. It's stuff that works automatically as opposed to things that we think about. So in the engineering context, then, we would say that governance is adaptive maintenance. We're saying that, okay, cool, the system isn't going to perfectly meet all of our needs forever, but we have a methodology, a cybernetic system, if you will, that makes sure that if the system's norms change, needs change, etc., that it's going to be able to adapt. And this can take a lot of different forms. If you have something like Bitcoin, really, you're often stuck with governance of last resort, things like forking. But in general, a healthy system is going to have the ability to adapt. And that is my last slide. So thank you very much. Yeah.
One of the most wonderful talks that we've seen the series here. And thanks for coming. Now, I know there are going to be a lot of questions, but give a disclaimer.
After the question, do not start the speaker. Reception outside, and I've seen the speaker with you sitting for like hours, being tired and traveling. So there's food for everybody outside, including our speaker. So if you get some questions right now, then we can go outside. I'm not going to drive it, of course. Any questions?
I want to start with a poll. So how many people thought that there was too much math? I'm serious, actually. I want to know. Okay, that's fine. How many people thought there was not enough math? Cool. Okay, so that means I did okay. At least I'm going to take the... I'm not going to ask the just right, because...
Cool. You know, I mean, the points we made, that were made, and that was very important and substantive. Yeah.
But anyway,
questions? Yes?
Where do you apply this? So, like, I mean, in which scenario?
By designing new blockchains or...
So the question is, where do we apply these things? And the answer is actually that because it's based on relatively general systems theory, we've applied it at multiple levels. So we've done analysis of the economics in low-level blockchain networks with clients, much of which is private because it's their IP. When my firm does analysis, we sort of build models for people and it's theirs, but we do economic analysis of the sort of protocol level economics when necessary. We can also do analysis of the like higher level economies. The way that we make this distinction is an enabling economy is sort of like a bot economy, like miners doing things to provide a platform. They're kind of below the API, if you will. We can also do analysis of systems above the API. We call this an enabled economy, and it's actually much closer to a multi-stakeholder business system where there might be 2 or 3 classes of business actor. You know, you can imagine it almost like an Uber model where you've got like a platform that provides something. That's what the below the API group is doing. And then some sort of transaction from party A to party B that's enabled. And there's a non-trivial economic thing going on because instead of charging a fee as Uber, you're actually like siphoning off potentially some value, sort of taxing it by a transaction fee and funneling it down to pay people who are providing that utility. Or you can actually have a more minting-based model where you don't charge people, but you add tokens in a minting process. Interestingly enough, that's directly analogous to fiscal and monetary policy in an economic system. So we do this sort of bottom level, top level, some mutual, and even the example that I showed you before was really more of a computational business model that had very little to do with crypto directly, except for that a smart contract enforced the rules, and that helped open up the computational method because we knew those things couldn't be violated. We only really have to test the assumptions around the things that can be different based on behavior. I don't know, does that help a bit?
Trying to understand, is it for startups trying to like smart contracts or real world?
Right. So my clients that I generally can't disclose, besides the ones that tell me that I can, and I showed you an example from a company called Fairmint that produced the continuous organizations, and they are a startup, and their business model is not necessarily blockchain dependent, but it uses one. I've also worked with SMEs where they're actually just new lines of business that we're analyzing. It's very much a data science class of tooling, so it just comes down to the problem statement, and some things are more feasible than others. Yes.
As I understand, you're trying to as the, like basically the blocks for modeling the systems in the economic context, right?
I am, so actually, yeah, so the question is, am I trying to use blockchain for modeling the system? Was it in another context or? Oh, in an economics context, yes. So
what I inferred from you're trying to build any generalization for any problem that would be able to model the transactions, right? So
yeah, essentially, so this is correct. So the base capability that we worked on was essentially differential equations for business and economic processes. But what we apply it to in the blockchain context is basically whatever it is that our clients are implementing. So they're creating a set of rules. They tend to be smart contracts or low-level protocols that enforce cryptographically certain facts, but then there's lots of other facts that are not enforceable. They have to do with behavior. So we're taking the sort of canonical approach of a control systems engineer where you separate what you know to be true from physics generally and what you don't know that you have to estimate or observe. And by making that separation, we're using relatively, it's literally general systems theory is the core methods that, and applying it to those specific cases. And they tend to be very economics oriented simply because people are building things on blockchain networks that share value through rules that are pre-stated and enforced. So I think the biggest challenge that we have is that the tooling is from a mathematical discipline that cares very little about what is being represented, but there's a very formal way of knowing whether you've done it well or done it correctly and what you can infer from it and what you can't. Sorry, yeah, go ahead.
you don't have to use a blockchain for that.
Oh, absolutely. Yeah, so there's nothing about what we're doing that is blockchain only. We are doing a lot of work in a blockchain setting, and we did some academic work to build a bridge between a blockchain and a state-space model in order to make it applicable. But in practice, we've also worked on business processes that don't have blockchains involved in them.
So
kind of building on the last question. So how useful do you think you build this mathematical model, the formalization of the blockchain and all this stuff? How useful do you think using the gap from micro to macro?
So actually, that's actually one of the main theses. So the question is, how useful is this kind of modeling for bridging the gap between micro and macroeconomics? And actually, maybe it's not necessarily the mathematical framework of the blockchain, but more the cross application of the engineering methodology. Because in engineering, we do this sort of abstraction hierarchy thing, where you like say, here's my low-level system, and I make a model that is really doesn't have anything to say about the high-level system. So I'll use the robotic systems. I worked on some navigation ones. And so the navigation systems know a really simple model of what the robot is, but it's good enough given the noise of the sensors and whatnot to meet its goals. But then that model is informed by a model of the mechanical and electrical systems that are still not granular. They're not saying exactly how it works, but they're good enough to meet the needs at that layer, and then down to things like microcontrollers that drive, say, an individual wheel is going to turn at a fixed rate given a fixed voltage input based on the microcontroller enforcing that. And then ultimately you're kind of stitching together the computer systems, the mechanical systems, and the electrical systems to achieve these sort of high level, I want this to go from point A to point B. That is actually the issue of bridging micro to macro. You can't have micro, macro. You often need a hierarchy that takes you from the micro phenomenon that you care about up to the macro phenomenon that you care about. That's going to be very contextual, actually, because you have to start with either a macro phenomenon that you wish to explain and work backwards, or sort of a micro phenomenon and sort of work up. And as you saw in my slides, what we actually generally do is kind of work from both ends at the same time until we get something coherent. A little bit louder. Oh. Which reference table?
And if you can share a reference model, what do you mean by share?
Which kind of previous work, which kind of you use?
Share the reference model.
So I don't know. Again, it depends. So for first, it kind of depends on what you count in the same bucket. Technically, what we're doing in a general system theory sense is in the tradition of cybernetics, which goes back to the 40s, the fact that we're doing these sort of multi-scale computational models that have both a sort of system dynamics and an agent-based, like integrated. I believe that we're the first ones doing this. There's probably other people doing things in parallel. I would expect it to be the natural consequence of the sort of growing amount of data available that we would build agent-based models in the context of dynamical systems. So I'll say, like, we're at least in the class of people who are figuring this out. In terms of sharing the reference cases, there is some of them are public on GitHub at BlockScience as the name of the organization, and then there's a couple different repos there. CAD-CAD itself is open source. There's some tutorials. Believe that Uniswap model is posted, and the code for the simulations on from the applied network science papers up there and a few others. We're actually working on building out more for people to learn and build on, because it's actually our goal to sort of grow this utilization. It's not our position that we need to sort of design every crypto network or even design every, every business system or whatever. It's actually just a acknowledgement that there's a degree of engineering practice that can be applied to economic and business systems that maybe wasn't possible before we had the combination of data and differential equations. I personally, again, being a controls engineer, am shocked that we haven't had sort of social science type differential equations, more integrated in our data science practice. But I think it just comes back to the fact that we're only really just learning to integrate the massive streams of data. And that's a little bit different from having the skills to build theoretical models that match, that aren't just black box. Yeah. That's totally true. So shout out to there's a Designing Tokenized Ecosystems report, and the author is here right now. Eden, you want to raise your hand? That guy. Is a really good primer for how to design these kinds of systems, and the work that we do at BlockScience is a bit downstream of that. So you really do have to have a well-defined system before it makes sense to do system modeling. As a team, we generally work through that representation problem with our clients so that the models that we run actually meet their needs as sort of decision makers.
Okay, one last question. We'll continue. I mean, all the self
And that's the last question myself. One more question.
Running, is it the problem that's inherent in the blockchain, or can the blockchain be designed to address it?
Front running is inherent in the sense that, like, as long as two actions have state dependence with respect to each other, meaning the current state of the system affects the outcome or the effect of the next transaction. So order matters. Even if you were to go to something like a DAG chain, those things would still be linked in the sense that they have dependence. So I will have to say that front running is inherent as long as one action has a bearing on another, though I believe that at the level of transaction ordering, there's this, there are questions about how to make sure that people can't manipulate the order. Order will always matter, so front running will always kind of be a thing, but if you can control the means by which the order is set, you may be able to mitigate the risk of front running attacks.
I got last question. Organize that.
Yesterday or today, depending what time zone you're looking at, it was announced the Open Libra framework, and you're one of the dozen of core members of that. So Open Libra, so Open Libra is like 1.5 days manifesto, if I can call it that, that they will, the consortium or the people will adopt the move language, but no more details on that.
Right? So
a couple of questions just summarize.
what you can
I'm trying to get the gossip out.
Yeah, I can tell.
Since we got it here. So is there
going to be a collateral?
is it going to be
Some kind of like
coin?
So where we're at right now is very simple. It's that if you notice when I talked about governance, I talked about the importance of the feedback loop between the participants, the constituents, the community members. So at its base, Libra is an incredibly powerful technology. It's very exciting in a lot of ways, but the ultimate governance feedback loop is broken in the sense that the only people that have the ultimate say over what contracts can be deployed and sort of any sort of decisions that we would call governance doesn't actually come back to either the user base or even necessarily the developer base. And so what this initiative is actually aiming to do is port the very powerful Move language which Facebook has put and the Libra consortium has put a lot of time, energy, very smart developers into creating, and actually they open sourced it, which is wonderful. And we basically decided that it shouldn't be that only people who are willing to build in that ecosystem where we have this sort of limited amount of say can benefit from Move. And so actually we're working with several people from the Cosmos ecosystem, actually some of whom actually live here in Toronto, to basically try to put Move on Tendermint, which basically means that we can have a public network with a lot of the same characteristics of Libra, and that Open Libra is a way of thinking about this as, making that technology that they open sourced and created available to people who maybe want to build something that they have governance over. The economic design stuff is actually like further down the roadmap. So if you look at the way that we architect systems, even from what I've talked about, you have to have essentially a state machine before you can build up to, because I did social, we've got economic, and we've got this sort of peer-to-peer communication and computation. And at its base level, Move is a smart contract writing language, and the Tendermint is the consensus engine. And until you get those things put together, it's not immediately time to start designing the additional economic logics.
adopt the move platform as a secure programming platform. Okay, so I will escort the gentleman outside for the start here. Thank you again for coming, and let's thank you again.